Hi guys, welcome back to my channel. Today let's talk about hydrodynamics. So this is the third video for my fluid series. In my first video, I talked about the basics of fluid. I think specific gravity is a pretty high yield topic. And then my second video, we talked about hydrostatics, right? All the equations, all the laws that I provide you are describing the fluids that are not in motion, they're static, right? Whereas today's video, hydrodynamics, meaning that everything is about the fluids that are in motion. They are moving. Okay, all right. So if you haven't watched the first two videos, these are the notes from my other videos. I will share the links in the description. All right, let's jump into today's topic. Okay, so first question, what is viscosity? Okay, all right. So viscosity is basically the fluid's property to be resistant to flow, right? So viscosity is basically being resistant to flow. Okay, as you can imagine, fluids, they have this natural spontaneous tendency to flow from high to low, from one point to another point, right? But sometimes there's some resistance. It's not that free for them to flow. And what is causing this resistance, or in other words, what is causing the viscosity, right? It's actually friction. Okay, so friction is a non-conservative force that is dependent on the path, right? So this friction between different layers of the fluids is really causing the viscosity, okay? It's slowing down the movement. Okay, perfect. So now let's talk about the unit of viscosity. What is the unit of viscosity? It's a Pascal times second, right? Times 10, time, okay? All right, so Pascal is basically what? Pressure, right? So I can also indicate it like a Newton and then meter squared, which is area, right? Certain force over area, that is pressure. Okay, times S. Okay, so this is the second unit for viscosity. Or I can break it down Newton even more. So Newton is really kg m second squared, right? And then if I plug in this to my second unit, then I get kg m second squared times S over m squared. And then that gives me kg ms. Okay, so all these three are units for viscosity, okay? All right, and then what is the symbol for viscosity, okay? So on MCAT, I usually see two symbols. One is kind of like a U, but it's really a Greek letter mu. And then also something like an N, but once again, it's not an N. It's a Greek letter. It's pronounced like an E, okay? So these are the symbols of viscosity that you may see on MCAT, okay? And then lastly is the viscosity's relationship with temperature, okay? So they have an inverse relationship. As temperature goes up, viscosity goes down, okay? It will basically travel faster, right? With less viscosity. Okay, all right. So now let's move on to laminar flow. Okay, what is laminar flow? As you can see here, this laminar flow is this a beautiful, everything's in order. They're going towards the same direction. So basically, laminar flow is a parallel flow, right? It is a parallel flow. Okay, it has parallel layers of flow, to be more specific. Okay, but one thing worth noting is that these parallel layers, do they travel at the same speed or different speed, right? Okay, this is a good question because a lot of misconceptions about the speed of the traveling speed, the flow velocity of these parallel layers, that people think, oh, they're travel at the same distance because everything is just perfect, everything is just so neat, right? But that's not the case, right? As you can tell that these velocity vectors here, some are longer, some are shorter, right? Really indicating the different magnitude of the velocity, okay? And then because there's a different magnitude of friction in between the layers, so that it causes different amount of viscosity, so that you will have a different speed, all right? So I should say they travel at different velocity. Okay, the layers travel at different velocity. All right. Okay, so now let's move on to something called Poiseuille's law. I'm not sure. This is French. I can barely pronounce a lot of the English words, not to say this French one. So, but basically this law, I'll call it P law. Okay, this P law describes flow rate, okay? So Q is flow rate. It's the volume flowing past a point in time, okay? So Q here, according to this P law, it's delta P times pi times r squared. R is radius, right? Over 8, and then this is viscosity times length of the vessel or tube, okay? So this is what describes the flow rate according to this P law. But on MCAT, you will never see that they give you a bunch of numbers and ask you to plug in and calculate a quantified answer for flow rate, right? They're more likely to test you on the relationship, right? And the relationship is really Q is proportional to what? Delta P and R, right? And it is improportionally related. It is inversely related to, viscosity and the length of the tube, right? Okay, so these are the relationships. It really makes sense, right? If you think about it, if the viscosity is super high, right? It's super viscous, then of course your flow rate will decrease. It will be harder, right, to flow. And then because flow rate is the volume, like I said, volume flowing past a point in time. So if the thing is the length is super long, then it takes longer time. Then it also is a inverse relationship, right? And then this R is the radius, right? So if this tube has a super wide cross-section area, it's the radius is big enough, then it's more free for the fluids to flow, so that your flow rate will increase. So it's a direct relationship, right? And then also delta pressure is basically what? Force over area. So if you have a large change of your force, right, exerted on area, then of course that meaning that it will flow faster. You have a higher flow rate, okay? So that's the logic, okay? So I've seen them having a question that how they test this is that they say, okay, we have some sort of tube or whatever vessel, okay? And then they have a machine, a sensor that senses the pressures at different points. So let's say when a fluid enters this tube, they test that the sensor shows the pressure is 40 Pascal, right? And then when a fluid exits this vessel, the sensor shows 60 Pascal, okay? And then all of a sudden, this sensor gives us a different number, okay? It's not 40 Pascal anymore. It's 20 Pascal, but 60 is still 60. So the question is asking, how does that indicate about flow rate, right? So all they're testing you is the relationship between delta P and Q, right? Because before the change, my delta P is what? Is 60 minus 40. That gives me 20 Pascal, right? But after the change, delta P is 60 minus 20. Now delta P is 40 Pascal. So you can see that the delta P really doubled, right? So if a delta P doubled, then what would Q do? Q would double as well. Okay, so that's a usual way that they test you. And then on MCAT, on the physics section, they tend to give you some super complicated equation, not necessarily this P law that you've seen, but they can modify it. They can give you different variables, right? And then just don't panic, don't freak out. You just sort out the relationship, okay? And then you're good from there. Okay, all right. So now let's move on to turbulent flow, okay? So turbulent flow, as you can see here, everything is not nice and neat anymore, right? They're going towards the different directions, and of course, they're traveling at very different velocities, right? Okay, and then this just messed up, right? And then I wonder if the fluids in the turbulent flow is traveling faster than the laminar flow, right? Actually, this is the case. The answer is yes, right? They usually travel faster. It's just they're just hectic, okay? All right, so everything's messed up, this turbulent flow. Okay, so now let's look at Reynolds number. So what is Reynolds number? So Reynolds number is actually a quantitative way for you to tell if this flow is laminar flow or turbulent flow, right? You can see the picture, say, this messed up picture is the turbulent flow. But if I don't show you the picture, I say, how do you tell the difference from a quantitative way? Then Reynolds number gives us this difference of if it's larger than 35, the Reynolds number is larger than 3,500, then it will be a turbulent flow, okay? If it's smaller than that, then it's a laminar flow, okay? And then this equation here that tells you how to calculate the laminar Reynolds number, this is not tested on MCAT, right? But I'm showing you this that you want to make the relationship makes sense to you, right? MCAT really asks you to plug in the numbers and calculate, but you want to know, okay, see, the Reynolds number when it's large, right, means it's a viscosity. This is viscosity is a low, right? Because it's this inverse relationship. And then when viscosity is low, as the Reynolds number is higher, that means that the thing is traveling, the fluids are traveling faster, right? Which is the case of the turbulent flow, okay? And then this density of the fluid is proportional to what? To the Reynolds number, right? Because I mean, if the fluid has a higher density, it kind of means like it has more ability to travel faster, right? Which is the case of a turbulent flow with a higher Reynolds number, okay? And then this is just velocity, okay? And then this, another V, this is not velocity. This is another symbol for a different kinetic viscosity, okay? This is called a bulk viscosity. But you don't have to go that deep, okay? All right, so now we can move on. Okay, and then this other equation, you don't have to memorize. I'm just showing you that how this Reynolds number is really dimensionless. Okay, all right, there's no unit for this, okay? All right, so this is about laminar flow and turbulent flow, right? Both flows, they have some viscosity in there, right? So that we say they're non-ideal. They're non-ideal fluids, right? Whereas the definition of ideal fluids that we're gonna apply for our continuity equation and Bernoulli's law that we're gonna talk in a second, they are really some fluids without ideal fluids are fluids without viscosity. And then they are also incompressible. All right, so these are the ideal fluids. Okay, so now we're ready to talk about continuity equation, okay? So continuity equation is really another Q, okay? This Q is just the same as that Q. They both describe flow rate, okay? So this is just a simpler equation that Q equals VA, okay? V is velocity, A is area, right? So you know that if I have a tube here, I have a 0.1 and 0.2, right? It's the same system, right? So your Q1 must equal to Q2, right? Because they're in the same tube, right? The flow rate is the same all the way through, right? So because Q1 equals Q2, then I know Q1 equals what? V1, A1, and then Q2 equals V2, A2. So these two must be equal to each other, right? So, I mean, here, you see that let me change my section area, okay? Let's say 0.2 is here. So that you see that A2 is larger than A1, right? Which means what? V2 has to be smaller than V1 to balance it out, okay? All right, so this is continuity equation. And then I said that this Peace law, they never ask you to calculate flow rate through this equation, this P law. But sometimes on MCAT, they do ask you to calculate the flow rate, but they want you to use this equation, continuity equation, okay? So you find the velocity, and then MCAT is never straightforward. I just tell you, oh, this is velocity, this is the area, and please calculate the flow rate, right? They would tell you the radius, right? And then you know the radius, and then you know if it's a cylinder, the cross-section area, it's a 2 pi r squared, right? So you have to calculate area from the r that's given, and then multiply by the velocity, and then you get the flow rate. And then this velocity you might not find it in a passage, but it's in the graph, right? It's in the table, things like that, okay? All right, so that's continuity equation. All right, so now I think we're ready for Bernoulli's law. Okay, I love this topic. Okay, this is one of my favorite MCAT topics. Okay, so are you ready for this? So Bernoulli's law, as you can see that we have 3 terms on the left and 3 terms on the right. So I'm going to call them this term 1A, and then this is B, this is C, okay? 3 terms on the left. And then on the right, A prime, B prime, C prime, okay? All right, so let's break it down each term, okay? What I want to show you is Bernoulli's law is nothing more than conservation of energy, right? And then I have to prove to you that A, B, C, all three terms, they're all energies, okay? How do I prove that to you? So let's take a look at here, okay? A, so A is my term A, right? So it's P, okay? P is what? P is pressure, okay? So pressure, as I've mentioned earlier in this video, it's really what? It's a Newton per meter second, right? I mean, this Newton should be capital letter. Okay, so Newton per meter squared, okay? So now if I times another m, okay, then I mean, it doesn't change, right? Because I can really cross it out, right? But if I don't cross it out, you see this n times meter gives me what? Gives me joule, right? Sorry. This is a Newton times meter. So that gives me joule. This is work, right? Force over a distance, over some distance. That gives me joule, right? And then this m squared times m, this is m cubed. This is volume, right? This is basically volume. Okay, so this term A pressure is basically what? It's basically work, pressure, energy, pressure, work over some volume, right? So, okay, so this A, I'll put it here. A is really pressure, energy, right? Work, I mean, I can't say work equals energy, but kind of, right? On MCAT. Okay, to be more precise, is work is the difference, the change of energy, delta energy, right? Okay, but I mean, this is enough for us. I hope that's enough to convince you that the term A is pressure energy, okay? And then let's take a look at a term B, okay? Okay, so term B is what? Is a 2/2 rho, this is density of the fluid, right? V1 squared, okay? This is all good, okay? This is all good. Let's forget about this for a minute. And then I want to remind you of the kinetic energy equation is 1/2 mv squared, right? So that's what you've utilized this equation a lot of times, right? When you did a kinematics, right? Okay, so you have to admit this is the kinetic energy, right? 1/2 mv squared. Okay, so now let's see how the magic happens, okay? So if I divide it over volume, so you see that this mass over volume is just what? It's just the rho here, right? It's just rho here, which means what? Which means this second term, this term B, is really the kinetic energy over volume, right? So the term A is pressure energy over volume. The term B is kinetic energy over volume. Okay, now let's look at C, okay? Term C is what? Is rho GH, okay? So I need to remind you another equation that you learned from the kinematics chapters, which is a potential energy, right? You've done a lot of potential energy problems and you know it's mgh, right? So once again, I just divide this by volume. And then you see that this m, mass over volume, is rho, is the density, right? So really, the term C is really the potential energy per volume, right? So all terms, term A, B, C, they're all some sort of energy, right? And then if I have this tube here, so I have this tube here, right? I have a 0.1, 0.2, 0.3, right? So it's like this 0.1 is really A, B, C, right? All three energies, because energy is conserved at 0.1 and 0.2 and 0.3. It's all the way conserved. So that at 0.1, I have a ABC right here. P1 times 1/2 rho V1 squared times a rho G H1, right? And then the 0.2 is really A prime, B prime, C prime, right? And then this 0.3, I mean, I can really just keep going, right? A plus B plus C, A prime plus B prime plus C prime. I can really keep going. P3 times 1/2 rho V3 squared times rho G H3, right? Which is A prime prime plus B prime 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 C prime prime, okay? So really, this is the conservation of energy, okay? All right, now let's look at the application. This I really provide you the very comprehensive all 4 applications of Bernoulli's law, how they can test you on MCAT, okay? So these 4 applications are, first one is a Venturi's effect, and then the second one is a pitot tube, and then pitot tube calculates the velocity of the flow, right? But besides pitot tube, they can also set up a different scenario that asks you to calculate the same thing. And then lastly, airplane. These 4 scenarios, let's look at Venturi's effect first, okay? So Venturi's effect is really basically taking advantage of Bernoulli's law, okay? Taking advantage of Bernoulli's law to come up with a vacuum, okay? So let me show you how so, okay? So I have this setup here, okay? So 0.1 is here, right? And then 0.2 is here, right? As you can see that 0.2 has a smaller radius than 0.1, which means what? The area, the cross-section area, A1 is larger than the cross-section area at 0.2, right? A1 is larger than A2, okay? Due to the different radius as I show in this picture, okay? And then our continuity equation says, okay, it's one system, right? The flow rate is all the way through. So V1 A1 equals V2 A2, right? And then because A1 is larger than A2, this means what? This means V1 has to be smaller, have be slower than V2, okay? And then this gives us this term B, and B prime, term B prime gives us relation this 1/2 rho V1 squared must smaller than 1/2 rho V2 squared, right? Because this rho, this density is the same. There's the same fluid, right? And their density is the same all the way through, right? So that this V1 V2 relationship gives me the relation of term B and term B prime, right? And then I can cross out this third, this C term and C prime, right? Why? Because they're like, it's not like 1 and 2, they have super different height, right? If a 0.2 is here, then you say, oh, this H1 is different than H2, but they're really at the same level. So I can cross out the third term, right? Term C, because like I said, the rho density is the same and G is just 10, right? So I mean, I can cross it out. So what I've left with is P1 and P2, okay? And then because my term B is smaller than B prime, so this P1 has to be really what? P1 has to be larger than P2, so that this equation, this Bernoulli's law, can establish, right? You can have this. You can say equal here, right? As do you see that this equal? Okay, so if P1 is larger than P2, okay, here P1 is larger than P2, more pressure here, right? Which means that if I have some whatever molecule, gas molecule in there, due to the P2 of the lower pressure, then these things can sneak out and actually go there, and then my beaker can collect it, okay? So it's like a vacuum that sucks out the molecules in this setting due to the lower pressure at point 2. Okay, all right. So this is a Venturi's effect. Okay, so now let's move on to P-TOT tube. Okay, so P-TOT tube is usually when they ask you to calculate the velocity of the flow. Okay, so how so? Let's see. Okay, so this is my setup. Okay, so my setup, let me actually open it up a little bit. So let me just cut it open here and then cut it open here, okay? All right, after I cut it open, let me send some flow. It can be airflow, it can be fluid flow, whatever flow, okay? So when a flow that goes there, we know that it would enter here, right? But it won't enter here due to the orientation, right? So you have some fluid going in there, okay? And then let's say that I have these two different tubes, right? So I'll say this is a tube 1, and then this is a tube 2, okay? I meant this is 1, this is 2, okay? All right. So that the thing that as it flows to the pressure detector, the sensor will tell me what is the P1, what is P2, right? So if I do the subtraction, I can know delta P, right? The difference of these pressure. I mean, this is just extra math you have to do, okay? So the point is that I can know the P1 and P2, okay? And then this setup, the location 1 and location 2, I mean, I can really cross out the C term, because they're really on the same level, right? Okay. And then I can really also cross out this term, okay? Why? Because as I said, the flow never entered here, from here, due to the orientation, right? It's only we only have V1, we don't have V2, because the flow never entered, right? And then the flow velocity that we're calculating is really this incoming flow velocity, right? So I crossed out this term, okay? So now what I'm left with is a P1 times 1/2 rho V1 squared equals P2, okay? That's it, okay? So V1 is the thing I'm calculating, right? If you manipulate the equation, then V1 eventually equals square root of 2 P2 minus P1 over rho, okay? So you know that P2 minus P1, you can just tell from the pressure detector, right? It's just delta P, different numbers that shows on this pressure detector. You do the subtraction and then you get this, right? You get this delta P, okay? And then the density of the fluid, maybe the passage will provide you, maybe it won't if the fluid is water, and then you're responsible for knowing the density of water on MCAT, so that if they don't provide you, you just know this rho, right? You know this density, and you plug in and you can calculate the flow velocity, okay? This incoming flow velocity. Okay, perfect. So this is the one setting, but there's a different setting that they can also test you the flow velocity. Okay, so let's draw it out. So let's say I have a beaker. Okay, so let me open it up a little bit here. Okay, so that this leaky part, right? I have fluids in there, so that this really some fluids can leak out, right, through this entrance. Okay, all right. And then my H1 is this, okay, H1, because this is a 0.1, okay, and then this is a 0.2, okay, so my H2 is such, okay, all right, so I want you to calculate V2. So when this fluid leaks out, what is a V2, okay, so this is also calculating the flow velocity, right? So how do we do that, okay? So we need to analyze the three terms again, okay? So in this case, we're not going to cancel out the third term because there's a H difference, right? H1, H2, they have different height, right? They're not on the same level. So we're not going to cross it out, but we're going to cross out this term. We're going to cross out the 1/2 rho V1 squared. Why? Okay, so let me show you. So as you can see here, like this little leaky part is really like have a very small sectional area, right? Whereas I have a larger area here at 0.1, so that you can tell that really A1 is way larger than A2, right? Okay, and then because A1 is way larger than A2, according to the continuity equation, that V1 is way less than V2. So V1 is, we ignore it. It's roughly equal to 0, okay? So that's why I crossed out this term, okay? All right. So now I crossed out that term, okay? So what else can I cross out? Can I cross out P1 and P2 here? Yes. Why? Because they're both on sea level or on a high mountain. It's not that 0.1, 0.2 have a big difference of latitude, right? It's one beaker. So I can cross out. They experience the same atmospheric pressure. So I can really, the pressure energy is really the same. So I'm going to cross out P1 and P2, okay? So what am I left with? I'm left with rho GH1 equals 1/2 rho V2 squared plus rho GH2, okay? And then I manipulate the equation, and then what I get is V2 equals square root of 2G H1 minus H2, okay? All right, so H1 minus H2 is basically, how do I word it in a different way? H1 minus H2 is this much, right? This much is basically the depth of this leaky entrance, okay? So I can also say, okay, it's just 2GD, right? Okay, so this is really worth 2 more minutes for us to talk about something else that I want to show you that how magical this equation is, okay? Because back in the days when you learned the kinematics, let's say there's a slope here, okay? Then you have this object, okay? So it has a V1 that I don't know, right? I want you to calculate. Then this is all the way down to the ground, okay? So it's like here on the ground, this is V2. V2 is 0, right? It stops, okay, when it reaches the ground, okay? So that we use the conservation of energy to calculate V1 back in the days, remember, right? So we will say, okay, the kinetic energy at 0.1, which is 1/2 mv1 squared, times the potential energy at 0.1, which is mgh1, right? Equals the kinetic energy at 0.2, which is 1/2 mv2 squared, and then plus the potential energy at 0.2, which is mgh2, right? And I can cross out this v2 because v2 it stops, right? It's 0 meter per second, so I can cross out that. And then what I've left with, and then I can also cross out the m, right? All the mass are the same. And then so I have this gh1 basically equals 1/2 v1 squared, and then my v1 squared equals 2gh, right? So my v1 equals square root of 2gh, right? You know that. And then you see how similar these two are, right? I mean, it makes sense. They're basically conservation of energy, right? It's just that these are box scenario. You don't have the term A, right? We don't take the pressure into account. But really, they're both conservation of energy. Okay, that's Bernoulli's law, okay? All right. Lastly is our airplane application, okay? So fluids are not just liquid. They can also be gas, right? Air molecules are gases. So really, we can also apply, airflow to the case of Bernoulli's law, okay? All right, so let's see how does this work, okay? So this is an airplane, right? And then this is the wing of the airplane. So the engineers, when they design the airplane, they kind of use more material for the wing, for the upper part of the wing, okay? So this part is above the wing, right? This is below the wing, okay? So because this part, they use more materials, more curved, so that when airflow travels, if they want to have the same flow rate, right, a continuity law, then due to the difference of their surface area, V above must be larger than V below, right? Okay, so I'll say this V above, let's say it's V1, and then this V below is a V2, okay? All right, so they have a different V, different velocity, okay? All right, and then what happens is the P can be, this can be crossed out. The rho GH, the term C can be crossed out because it's really just the wing, right? You have the same amount of similar height, right? It's not that the wing is super thick, right? So we can neglect the H, right? So we can cross out this term, okay? Okay, then because we crossed out the third term and then the second term, there's a difference, right? This term B is larger than this term B prime, right? And then this tells what? This tells you this P1 must be what? Must be smaller than P2, all right? And then there's a delta P. The difference of pressure is what lift up the airplane, okay? All right, that's the level of depth that you need to know for MCAT. And then when I was talking about laminar flow, I forgot to relate it to some biological application, okay? So let me go back to laminar flow really quick. So I used to work for an OR for my pre-med clinical experience. And then on my first day of training, my trainer told me that, look at those orthopedic OR. And then if you have to be in the OR during the surgery, you have to scrub in, please do not, you're just gonna hang out with the anesthesiologist. You cannot go to the other side of the OR because there's laminar flow, and she meant airflow, right? There's laminar airflow that's coming out, okay? So I was like, oh, I know what is laminar flow, right? It's all this beautiful thing. So I was thinking, okay, is it because if I enter the area, I'm gonna break this beautiful balance, right? But it doesn't matter because if once I left, well, the flow will get back to this beautiful, nice setup, right? But the truth is actually it's not that I go into the laminar flow area that breaks this beautiful balance. It's actually the true application that this laminar airflow technology in OR is to really just enhance the air quality, to minimize the germs that can cause infection, right? So if I enter this laminar airflow area, then I could bring germs, right, that can cause infection. So that's why, okay? All right, so I thought that's related, okay? All right, so that's all I have for you for hydrodynamics, right? If you have some questions, you can leave me a comment down. Please subscribe or like my video if you think that's helpful.